Here is a question that sounds simple and turns out to be the largest one a human being can ask. Where did all of this come from? Not your house or the earth or even the stars, but everything, all of it, the entire universe, the whole stage that space and time and matter play out on. And along with it come two more questions just as enormous. What is the universe actually made of underneath everything we can see? And how does it end? For almost all of human history, these were questions for myth and religion because there was simply no way to investigate them. But over the last 100 years or so, something astonishing has happened. These questions have become science. We can now point instruments at the sky and gather real, hard evidence about the origin, the contents, and the fate of the entire cosmos. And we have built actual theories, testable ideas, that try to explain the whole thing. This is a tour of those theories, every serious idea humans currently have for explaining the universe, from the well-established to the wildly speculative. Some of what you are about to hear is as solid as anything in science, backed by mountains of evidence. Some of it is brilliant, careful guesswork at the very edge of what we can test. And some of it crosses into ideas we may never be able to prove or disprove at all, which raises its own deep question about where science ends and philosophy begins. I will try to be honest throughout about which is which, because one of the most important and least appreciated facts about cosmology is how much we genuinely do not know and how comfortable good scientists have learned to be with saying so. So let us start by being clear about what we even mean by the universe, because it is slipperier than it sounds. In the simplest terms, the universe is everything that exists, all of space and time, and everything in it, all the matter and energy, and the laws they obey. But there is a crucial catch, which is that we cannot actually see all of it. Because light travels at a fixed speed and the universe has been around for a finite time, only about 13.8 billion years, we can only see objects whose light has had time to reach us. There is a horizon, a bubble around us beyond which we simply cannot see, not because nothing is there, but because the light from those places has not arrived yet and, due to the expansion of space, in many cases never will. Everything inside that bubble is what we call the observable universe, and it is a sphere roughly 93 billion light years across. What lies beyond it, we do not and perhaps cannot know. The whole universe may be vastly larger than the part we can observe, and it may even be infinite, stretching on without end. So when cosmologists talk about the universe, they usually mean the observable part, while still acknowledging that it might be a tiny sample of something far greater. There is one more idea we need before we can do any cosmology at all, and it is so important that the whole field rests on it. Yet it is just an assumption, a very well tested one, but an assumption nonetheless. It is called the cosmological principle, and it says that on the largest scales, the universe looks essentially the same everywhere and in every direction. Not locally, of course, because locally there are stars and galaxies and great empty voids, lots of lumps and gaps. But if you zoom out far enough, averaging over enormous stretches of space, the universe becomes smooth and uniform, with roughly the same amount of stuff and the same kind of structure no matter where you are or which way you look. This matters enormously because it means our little corner is not special, that what we see around us is a fair sample of the whole. Without this assumption, we could never reason about the entire universe from our one vantage point. With it, the universe becomes something we can actually build theories about, and remarkably, every test we have done agrees that it really is, on the grandest scale, astonishingly uniform. Once you accept those two ideas, that the universe has an observable horizon and that it is uniform on large scales, you can start asking the big three questions in a scientific way. Where did it come from? Meaning, how did it begin and evolve into what we see? What is it made of? Meaning, what are the ingredients that make up the cosmos as a whole? And where is it going? Meaning, what is its ultimate fate? Over the next stretch, we are going to walk through humanity's best answers to each of these, the leading theory and its rivals, the solid science and the wild speculation, and we will end up at the very frontier, in territory where the honest answer to every question is that nobody knows yet. It is one of the great intellectual adventures of our species, and the remarkable thing is that we have gotten as far as we have. So let us begin where the universe itself begins, with the single most important and most thoroughly tested idea in all of cosmology, the theory of how everything started. The leading theory of the origin of the universe is, of course, the Big Bang, and it is worth understanding both what a triumph it is and what it actually claims, because it is one of the most misunderstood ideas in all of science. The story really begins with a discovery we have met before, that the universe is expanding. When astronomers looked out at distant galaxies in the early 20th century, they found that almost all of them are racing away from us, and the farther away a galaxy is, the faster it flees. This was worked out from the theory by a Belgian priest and physicist, and confirmed by observation not long after, and it changed everything, because an expanding universe has an obvious and stunning implication. If everything is flying apart now, then in the past everything was closer together, and if you run the film backward far enough, all the matter and energy in the cosmos must once have been packed into an unimaginably hot, dense state, from which it has been expanding and cooling ever since. That hot, dense beginning and the expansion that followed is the Big Bang. Now, here is the single most important thing to understand about the Big Bang, the misunderstanding that trips up almost everyone. It was not an explosion that went off at some particular point in pre-existing empty space, flinging matter outward into the void. That picture is wrong. The Big Bang was the expansion of space itself, happening everywhere all at once. There was no center, no special spot where it happened, because every spot was the spot. Space was not empty and waiting to be filled. Space itself was part of what was expanding, stretching like the surface of a balloon being inflated, with the galaxies riding along as the space between them grows. This is why there is no edge to point to and no center to find. The Big Bang happened here, where you are sitting, just as much as it happened in the most distant galaxy, because all of space was once compressed together, and all of it has been expanding ever since. The reason the Big Bang is accepted by essentially every cosmologist is not faith or fashion, but evidence, and it rests on three great pillars that all point the same way. The first is the expansion itself, the observed flight of the galaxies, which directly implies a denser past. The second is the afterglow. If the early universe was incredibly hot, then it should have been filled with intense radiation, and as the universe expanded and cooled over billions of years, that radiation should still be around today, stretched out into a faint, cold hiss of microwaves coming from every direction in the sky. This afterglow, called the cosmic microwave background, was discovered in the 1960s, exactly as predicted, and it is the single strongest piece of evidence we have. The actual baby picture of the cosmos, light from when the universe was only a few 100,000 years old. The third pillar is the recipe of the lightest elements. The theory predicts that in the first few minutes, when the whole universe was hot enough to act like the core of a star, specific amounts of the lightest elements, mostly hydrogen and helium, should have been forged in a very precise ratio. And when we measure the most ancient, untouched gas in the universe, we find exactly those proportions. Three completely independent lines of evidence, the expansion, the afterglow, and the elements, all agree on the same hot, dense beginning, which is why the Big Bang is as solid as any theory in science. But it is just as important to understand what the Big Bang Theory does not claim, because this is where the misunderstandings and the overreaching begin. The Big Bang Theory describes how the universe evolved from a very early hot, dense state up to the present day, and it does this superbly. What it does not do, despite its name, is explain the very first instant, the moment of creation itself, or what, if anything, came before. The theory works beautifully from a tiny fraction of a second after the beginning onward, but at the very first moment, when everything was compressed to a single point of infinite density, our physics breaks down completely and gives nonsense, because that is exactly the situation, the very small and the very heavy at once, where our two great theories, general relativity and quantum mechanics, refuse to work together. So, the Big Bang Theory is not really a theory of how the universe began from nothing. It is a theory of how the universe developed after the beginning. The actual first instant and the question of why there is anything at all sit just beyond its reach, in territory where the leading idea picks up the story a hair's breadth after the start, but cannot quite touch the start itself. That gap is where some of the most fascinating and speculative theories rush in, and we will get to them. It is worth pausing on how recent and how hard won this whole picture is, because it is easy to take for granted. The idea that the universe had a beginning at all, that it has a finite age and a history, was deeply controversial and resisted even by some of the greatest scientists who found the notion of a beginning philosophically uncomfortable and preferred to imagine an eternal, unchanging cosmos. The evidence forced the issue, and it is a genuinely strange and wonderful thing that we, small creatures on one planet, can look out and measure the age of everything around 13.8 billion years and reconstruct in detail what the universe was doing in its first few minutes. The Big Bang is not a story we made up. It is a conclusion the evidence dragged us to, often against our own preferences, which is exactly what gives it its authority. But for a long time, it was not the only serious idea on the table, and to appreciate why it won, it helps to meet the rival theory that fought it for decades and very nearly held its ground. For several decades, in the middle of the 20th century, the Big Bang was not the obvious winner it seems today, because there was a serious, elegant rival theory supported by some of the finest minds in science, and the contest between them is one of the great stories of how science actually works. The rival was called the steady state theory, put forward in the year 1948 by a trio of brilliant scientists, the most famous of whom was Fred Hoyle. They were deeply uncomfortable with the idea of a universe that had a beginning, finding it suspiciously close to a creation myth and philosophically unsatisfying. So, they proposed an alternative that kept the observed expansion but did away with the beginning entirely. In their picture, the universe is eternal, with no start and no end, and it looks essentially the same, not just everywhere in space, but at every moment in time. It always has looked and always will look, much as it does now. But this raised an obvious problem. If the universe is expanding, with galaxies flying apart, then, over time, it should be getting emptier and thinner, which would mean it looks different in different eras, contradicting their idea of an unchanging cosmos. Their solution was bold and strange. They proposed that new matter is continuously created out of nothing, everywhere, all the time, at an incredibly slow rate, just fast enough to fill the gaps left by the expansion, so that the overall density of the universe stays constant forever. The amount needed was tiny, just a few atoms per enormous volume of space per long stretch of time, far too little to ever notice directly, but enough to keep the universe eternally the same. It was a clever, self-consistent idea, and to many it felt more appealing than a universe that simply switched on one day for no reason anyone could explain. There is a delightful irony buried in this rivalry, which is that the term Big Bang itself was coined by Fred Hoyle, the great champion of the opposing theory, and he meant it dismissively. During a radio broadcast trying to describe the rival idea of a universe that began in a sudden event, he called it this Big Bang, mainly to draw a vivid contrast with his own theory, though whether he truly meant it mockingly is disputed, contrasting it with his own steady, dignified, eternal cosmos. The name stuck far better than the clumsy technical terms, and so the most important theory in cosmology ended up named by its biggest opponent as a kind of insult. Hoyle never accepted the Big Bang, arguing against it for the rest of his life, long after most of his colleagues had been won over by the evidence. and it was evidence, not argument, that settled the matter, which is exactly how it should be. The two theories made genuinely different predictions, and that is what made this real science rather than mere philosophy. The Big Bang predicted that the universe used to be hotter and denser, which meant that when we look at very distant objects whose light is very old, we should see the universe as it was long ago, looking different from how it is nearby, with more crowding and more violence in the distant past. The steady state theory predicted no such thing, since the universe should look the same in all eras. Observations of distant galaxies began to favor an evolving universe, but the killing blow was the discovery of the cosmic microwave background in the 1960s, that faint afterglow of a hot beginning. The Big Bang had predicted it. The steady state theory had no way to produce it and no place for it. With that single discovery, the debate was effectively over, and the steady state theory, for all its elegance, was abandoned. There is a real lesson in this, and a generous one. The steady state theory was not foolish, and the people who proposed it were not cranks. They were excellent scientists, responding to a genuine discomfort with the idea of a beginning, and they built a careful, testable alternative. Science needs rivals like this, because a theory only earns our confidence by beating real competition, by making predictions that come true where its rivals fail. The Big Bang is strong precisely because it had a worthy opponent and won on the evidence, not by decree. And Fred Hoyle, wrong as he was about the origin of the universe, was spectacularly right about something else, because he was the one who worked out in beautiful detail how the heavier elements are forged inside stars, the very process that made the carbon in your body and the oxygen you breathe. He earned a permanent place among the greats while being famously, stubbornly wrong about the biggest question of all, which is a useful reminder that being mistaken about one enormous thing does not make a scientist a fool, and that the history of cosmology is full of brilliant people confidently believing things that turned out not to be so. As triumphant as the Big Bang theory is, it left behind a couple of nagging puzzles that bothered cosmologists deeply, and the attempt to solve them led to one of the most important and most mind-stretching ideas in modern cosmology, the theory of cosmic inflation. To understand why inflation was proposed, you have to understand the puzzles it was meant to fix. The first is called the horizon problem, and it comes from that afterglow of the Big Bang. When we measure the temperature of the cosmic microwave background across the whole sky, we find it is astonishingly uniform, the same temperature in every direction to an extraordinary degree of precision. That sounds reasonable until you realize that regions on opposite sides of the sky are so far apart that in the ordinary Big Bang story, they could never have been in contact, never have exchanged heat or light, because there simply was not enough time since the beginning for any signal to travel between them. So how did they end up at exactly the same temperature as if they had carefully evened out together when they should never have been able to communicate at all? It is like finding two cups of coffee on opposite sides of a building at precisely the same temperature, with no way they could ever have touched. The second puzzle is called the flatness problem, and it concerns the overall geometry of the universe. According to general relativity, space can be curved, and the universe could, in principle, be shaped in different ways, depending on how much matter and energy it contains. It could be curved like the surface of a ball, or curved the opposite way like a saddle, or it could be perfectly flat, balanced exactly on the knife edge between the two. When we measure it, the universe appears to be flat, or extraordinarily close to it. And that is suspicious, because flatness is an unstable, balanced condition. If the early universe had been even slightly off from perfectly flat, that deviation should have grown enormously over billions of years, leaving us with a wildly curved universe today. For it to look so flat now, it must have been flat to an almost unbelievable precision at the beginning, and that fine balance cried out for an explanation rather than just being accepted as a lucky coincidence. The solution, proposed by a physicist named Alan Guth around the year 1980, was as audacious as it was elegant. He suggested that in the very first tiny fraction of a second, far less than a trillionth of a second after the beginning, the universe went through a brief burst of almost unimaginably fast expansion, ballooning in size by a staggering factor in an eye blink, far faster than the ordinary expansion that followed. This is inflation, and it solves both puzzles at a stroke. The horizon problem vanishes because the entire region we can see today grew out of a tiny patch that was small enough to have evened out its temperature before inflation suddenly stretched it to enormous size, which is why opposite sides of the sky match. They were once in contact, then flung apart, and the flatness problem vanishes because inflating something by such a colossal factor flattens it, the way blowing up a balloon to the size of the Earth would make any patch of its surface look flat, no matter how it started. Inflation does something else remarkable, something that turned it from a clever fix into a theory with real predictive power. Before inflation, the tiny patch that became our universe would have had small random quantum fluctuations in it, the unavoidable jitter of the quantum world. Inflation would have stretched those microscopic fluctuations to astronomical size, freezing them into the fabric of the cosmos as slight variations in density, places where matter was very slightly more or less concentrated. And those slight variations would then act as the seeds of all the structure we see today, because the denser spots would pull in more matter by gravity and eventually grow into galaxies and clusters of galaxies. In other words, inflation predicts that the largest structures in the universe grew from the tiniest quantum wiggles blown up to cosmic scale. And astonishingly, when we map the cosmic microwave background in detail, we find exactly the pattern of slight temperature variations that inflation predicts, the fingerprints of those stretched quantum seeds. This is a major reason inflation is widely accepted, because it made a specific prediction that the data confirmed. But It is important to be honest because inflation, for all its successes, is not on the same rock solid footing as the Big Bang itself. We do not know what actually drove inflation, what kind of energy field powered that burst of expansion, and there are different versions of the theory making different detailed predictions, some of which have not been confirmed. It remains an extension of the Big Bang rather than a settled certainty, an idea that explains a great deal and has passed some real tests, but whose deepest details are still debated at the frontier. And inflation carries a strange and profound implication that we will return to later, because in many versions of the theory, once inflation starts, it never completely stops everywhere at once. It keeps going in some regions even as it ends in others, endlessly spawning new, expanding patches, new universes, bubbling off forever. If that is right, then our entire observable universe is just one bubble in an unimaginably vast and eternally growing sea of other universes, most of which we can never see or reach. That idea, the inflationary multiverse, is one of several roads that modern cosmology has found leading toward the staggering possibility that our universe is not the only one. Now that we have the broad theory in place, it is worth walking through what the Big Bang model actually says happened, step by step, because the detailed story of the universe's first moments and early life is one of the most remarkable narratives science has ever assembled, reconstructed from physics and confirmed by observation. It begins at a moment we cannot quite reach, the very first sliver of time, often called the Planck era, lasting an almost inconceivably tiny fraction of the first second, during which the whole universe was so hot and so dense that all four forces of nature were likely merged into one, and our physics simply cannot describe it, because that is exactly where general relativity and quantum mechanics collide and break down. This is the genuine edge of knowledge, the curtain we cannot yet see behind. After that came the burst of inflation we discussed, that fraction of a second of staggering expansion that smoothed and flattened everything and planted the quantum seeds of future galaxies. When inflation ended, the energy that had driven it flooded the universe with a searing hot soup of the most basic particles, far too hot for anything stable to form. There were no atoms, no protons, no neutrons, just a roiling plasma of the universe's most elementary pieces, quarks and the particles that carry forces, slamming into one another at unimaginable temperatures. As the universe expanded and cooled in those first fractions of a second, the single unified force split apart into the separate forces we know today, gravity and electromagnetism, and the two nuclear forces, each freezing out as the temperature dropped, like steam condensing into water and then ice as it cools. Within the first millionth of a second or so, the universe had cooled just enough for the quarks to clump together into protons and neutrons, the building blocks of atomic nuclei. Then, over roughly the first 3 minutes, something wonderful happened in an event we have met before, the cooking of the first elements. The universe was still hot and dense enough to act like the core of a giant star, fusing protons and neutrons together into the nuclei of the lightest elements, mostly hydrogen and helium, in a precise ratio that the theory predicts and that we still measure today in the oldest gas in the cosmos. After those first few minutes, the universe had cooled too much for fusion to continue, and the basic recipe of ordinary matter was set, overwhelmingly hydrogen and helium, the raw material from which every star and galaxy would later be built. Everything heavier, all the carbon and oxygen and iron, would have to wait hundreds of millions of years to be forged inside stars. For the next several 100,000 years, the universe was a hot, glowing fog. It was filled with a dense plasma of bare nuclei and free electrons, and light could not travel freely through it because it kept bouncing off all the loose electrons, the way light cannot pass through a thick fog. The universe was opaque, glowing like the inside of a star. Then, around 380,000 years after the beginning, came a turning point called recombination. The universe had finally cooled enough to a few thousand degrees for the electrons to settle down and join with the nuclei to form the first complete, stable atoms. And the moment the loose electrons were swept up into atoms, the fog cleared and light could suddenly stream freely across the universe for the first time. That light, released at the moment the universe became transparent, is exactly the cosmic microwave background we detect today, stretched and cooled by billions of years of expansion. When you look at that afterglow, you are seeing the universe at the instant it became clear, the oldest light there is, a snapshot of the cosmos at 380,000 years old. After recombination came a long, quiet stretch that cosmologists call the cosmic dark ages. The universe had gone transparent, but there were no stars yet, nothing shining, just vast clouds of hydrogen and helium gas drifting in the dark, very slowly being pulled together by gravity, with the invisible dark matter providing the gravitational scaffolding, clumping first and drawing the ordinary gas into the densest spots. Over tens and then hundreds of millions of years, those clumps grew, compressed, and heated, until finally, somewhere around a couple 100 million years after the beginning, the first stars ignited, blazing into life and ending the dark ages, flooding the universe with starlight for the very first time. Those first stars were giant, and they lived fast and died in tremendous explosions, forging the first heavy elements and scattering them into space. Gravity kept gathering stars into the first galaxies, galaxies into clusters, and clusters into the vast cosmic web of filaments and voids that structures the universe today. Billions of years passed. Generations of stars lived and died, enriching the cosmos with heavier elements, until around 9 billion years after the Big Bang, in one ordinary galaxy, in a cloud enriched by the deaths of earlier stars, our own sun and its planets formed, including the small rocky world we are standing on. The entire chain, from a featureless hot plasma to a planet with creatures capable of working all of this out, is written into the Big Bang model, and astonishingly, the new telescopes peering at the most distant, earliest galaxies are now testing this very story, watching the early universe directly, and mostly finding it unfolds much as the theory says, with a few genuine surprises that are keeping cosmologists busy. It is worth stepping back to appreciate the framework that all of this cosmology is built on, because every theory we have discussed, the Big Bang, the expansion, the geometry of space, the fate of everything, ultimately rests on a single magnificent theory, Einstein's general relativity. Before Einstein, gravity was a force, an invisible pull between masses, and space and time were just a fixed, unchanging stage on which events played out. Einstein overturned that completely. In general relativity, gravity is not a force at all, but the bending of space and time, woven together into a single flexible fabric called space-time, and matter and energy warp that fabric, while the warping, in turn, tells matter how to move. This is the tool that makes cosmology possible, because for the first time it let scientists write equations not just for objects within space, but for space itself, for the whole universe, as a single dynamic thing that can expand, curve, and evolve. When Einstein and others applied these equations to the entire cosmos, the equations insisted that the universe could not sit still, that it must be either expanding or contracting, which is precisely what we later found. The expanding universe, the curved geometry of space, the very idea that the cosmos has a shape and a history, all of it flows from treating space-time as a thing that bends and stretches according to what it contains. With that framework in hand, one of the great achievements of modern cosmology has been explaining how the universe got from its smooth, featureless beginning to the richly structured cosmos we see today, full of galaxies and clusters and vast empty voids. The starting point is something we can actually measure, because the afterglow of the Big Bang shows us that the early universe was astonishingly smooth, the same temperature in every direction to about 1 part in 100,000. But it was not perfectly smooth, and that tiny imperfection is everything. Those minuscule variations, the slightly denser and slightly emptier patches planted by quantum fluctuations during inflation, were the seeds. In a denser than average spot, gravity pulls a little harder, drawing in more matter, which makes the spot denser still, which makes it pull harder yet, in a runaway process that, over billions of years, amplifies the faintest initial ripple into a galaxy, a cluster, a great structure. Gravity is an engine that turns tiny differences into enormous ones, and the structure of the entire universe grew from the gentle amplification of those primordial wrinkles. Dark matter plays a leading role in this story, which is one of the strongest reasons we believe it is real. Because dark matter does not interact with light, it was free to start clumping under gravity very early, while the ordinary matter was still a hot, glowing plasma being pushed around by radiation and unable to collapse. So, the invisible dark matter built the scaffolding first, gathering into a vast cosmic framework of dense regions. And then, once the universe cooled and the ordinary matter was released, that ordinary gas fell into the gravitational wells the dark matter had already dug, lighting up as stars and galaxies along the framework that was already there. The luminous universe we see, all the glowing galaxies, is in a sense just the visible decoration draped over an invisible structure that dark matter laid down first. Without dark matter to provide that early scaffolding, there would not have been enough time for galaxies to form as we see them. The result of all this is the largest pattern in existence, the one we touched on earlier, the cosmic web. The galaxies are not scattered evenly through space, but are strung together along immense filaments and sheets, threads of thousands of galaxies surrounding vast, nearly empty bubbles of nothing called voids. The whole thing resembling a three-dimensional web or a network of soap bubbles spanning the observable universe. And here is a beautiful confirmation of our understanding. When cosmologists run enormous computer simulations, starting with the smooth early universe revealed by the afterglow, adding in the right amounts of ordinary matter, and dark energy, and then letting gravity do its work over simulated billions of years, the simulations grow a cosmic web that looks strikingly like the real one we map in the sky. The fact that we can start from the baby universe and, using just our theories of gravity and the contents of the cosmos, fast forward to grow a realistic universe full of the right structures is one of the most powerful pieces of evidence that the overall picture is correct. We understand in real detail how a nearly smooth beginning became a cosmos of galaxies and our own place in it, a galaxy in a small group on the outskirts of a great supercluster. One node in the vast web is just an ordinary spot in that grand structure. There is a puzzle hidden in that early history that is so deep it touches on why we exist at all, and it is called the matter-antimatter problem. Recall from the story of physics that every particle of matter has an antimatter twin, identical but with opposite charge, and that when a particle meets its antiparticle, the two annihilate completely, vanishing in a flash of energy. Now here is the trouble. As far as our best understanding goes, the hot early universe should have produced matter and antimatter in exactly equal amounts, perfectly balanced. But if that were truly the case, then every particle of matter would have found an antimatter partner and annihilated, leaving a universe containing nothing but light. No atoms, no stars, no galaxies, no us. The very fact that anything material exists at all is, on the face of it, a mystery, because by the simplest accounting, everything should have canceled out to nothing. The resolution must be that the balance was not quite perfect. It seems that for every billion particles of antimatter in the early universe, there were about 1,000,000,001 particles of matter, the tiniest imaginable excess. When the great annihilation happened, every antimatter particle paired up and vanished with a matter particle, but that 1 in 1 billion surplus of matter had no partner left to annihilate with, and so it survived. And that minuscule leftover is everything. Every atom in every star, every planet, every living thing is made from that tiny rounding error, the 1 part in 1 billion of matter that happened to exceed the antimatter. We are, quite literally, the survivors of a near total cancellation, the faint residue left when almost all the matter and antimatter in existence destroyed each other in the first moments. Why there was that slight imbalance? What process in the early universe favored matter over antimatter by that razor-thin margin is still not fully understood. We know it must have happened because we are here, but the exact mechanism remains one of the open problems at the boundary of cosmology and particle physics. This leads naturally to the deepest question anyone can ask, the one that sits underneath all of cosmology and may lie forever beyond it, which is simply, why is there something rather than nothing? Even if we trace the universe all the way back to the Big Bang, even if we explain inflation and the matter surplus and every detail of the early universe, we are still left facing the ultimate question of why there is a universe at all, why there is something for the laws of physics to act upon rather than just empty, eternal nothing. For most of history, this was considered a question purely for philosophy and religion, entirely outside the reach of science. But in recent decades, some physicists have argued that science can at least begin to chip away at it, and their attempts are fascinating even if they do not fully succeed. The key insight they lean on comes from quantum physics, which tells us that empty space is not truly empty at all. Even a perfect vacuum, with all matter and radiation removed, is, according to quantum theory, a seething, restless place, with particles constantly flickering in and out of existence, borrowing energy for the briefest instants before vanishing again. Nothingness, in the quantum sense, is unstable and active. Building on this, some physicists have proposed that the universe itself could have come into being through a similar quantum process, that the entire cosmos might have spontaneously appeared, tunneling into existence out of a quantum state in a way that, remarkably, may not even violate the conservation of energy. Because when you carefully add up the positive energy of all the matter and the negative energy stored in gravity, the total energy of the universe might come out to very nearly zero. In that sense, a universe might be, energetically speaking, something you can get for free, a fluctuation that costs nothing overall. But it is important to be honest about the limits of this, because the moment you say the universe arose from a quantum vacuum, the obvious objection lands immediately, which is that a quantum vacuum, with its laws and its restless activity, is not really nothing. It is already something, a stage with rules. So, these ideas, clever as they are, may push the question back a step rather than truly answering it, replacing why is there a universe with why is there a quantum vacuum with these particular laws. Philosophers have pointed this out sharply, and the debate over whether science can ever explain why there is anything at all, or whether that question is simply outside what science can address, remains genuinely unresolved. It may be that this is the one question that no theory, however complete, can ever fully close, the bedrock mystery beneath all the others. And there is something fitting about that the largest question of all, asked by creatures made from a 1 in a billion scrap of leftover matter, may be the one we are never quite able to answer. So That is roughly where we are on the question of how the universe began and took shape. Now we turn to the second great question: what the universe is actually made of. And here the modern answer is so strange and so humbling that it deserves to be far more famous than it is. The complete standard model of cosmology, the one that fits all the data, is usually called the Lambda CDM model, an unlovely name that hides a genuinely shocking picture. It says that everything you have ever seen, every star, every planet, every galaxy, every atom in your body and in the earth and in the sun, all the ordinary matter in the entire universe adds up to only about 5% of what is actually out there. The other 95% is made of two completely mysterious things that we have never directly seen and do not understand, which we call dark matter and dark energy. We have built a precise, successful theory of a universe that is almost entirely composed of stuff we cannot identify. Dark matter makes up roughly a quarter of the universe, around 5 times as much as all the ordinary matter combined, and we know it is there because of its gravity. When astronomers measure how galaxies spin, the stars at the outer edges move far too fast for the visible matter to hold them in, and the galaxies should fly apart, yet they do not, which means there must be a great deal of unseen mass providing the extra gravitational glue. We see the same thing in how galaxies move within clusters, in how light from distant objects is bent by invisible mass along the way, and in the very pattern of the cosmic microwave background, all of which point to vast amounts of some kind of matter that has gravity but gives off no light at all, that does not shine, does not block light, and does not seem to be made of atoms like everything we know. Despite enormous, dedicated experiments, we have never directly caught a single particle of it. We have ideas about what it might be, exotic particles left over from the early universe, but after decades of searching, dark matter remains a confirmed presence and an unsolved identity. The invisible scaffolding on which all the visible galaxies are hung. Dark energy is stranger still, and it makes up the largest share of all, roughly 2/3 of everything. Its story begins in the late 1990s when astronomers measuring the expansion of the universe expected to find it gradually slowing down because the combined gravity of all the matter should be pulling everything back together and putting on the brakes. Instead, to their astonishment, they found the opposite. The expansion of the universe is not slowing down, it is speeding up. Something is pushing space apart faster and faster, overwhelming the inward pull of all that gravity, and we have no idea what it is. We call it dark energy, and the name is really just a label for a profound mystery. The leading idea is that it is a kind of energy belonging to empty space itself, a property of the vacuum, often represented in the equations by a term Einstein had once introduced and then abandoned: the cosmological constant, the Greek letter lambda that gives the standard model its name. Einstein had added that term and then called it his greatest blunder, and decades later it came roaring back as possibly the dominant feature of the entire cosmos. There is a genuinely embarrassing problem lurking here, one that physicists sometimes call the worst prediction in the history of physics. And it is worth knowing about because it shows how deep our ignorance really runs. If dark energy is the energy of empty space, then quantum physics ought to be able to calculate how much energy empty space should contain, since the quantum world says the vacuum is not truly empty, but seething with fleeting activity. When physicists do that calculation, they get a number for the energy of the vacuum that is larger than the amount we actually observe by a factor so vast it is almost impossible to write down. A number with 120 zeros after it. Our best theory of the small and our best theory of the large disagree about the energy of empty space. By the largest margin, any two scientific predictions have ever disagreed about anything. So we have a name for dark energy, and we can measure its effects with great precision. But our attempt to explain what it actually is produces one of the most spectacular failures in all of science. This is not a minor footnote. It is a flashing sign that something deep in our understanding is missing. Put it all together, and you arrive at the strange portrait of the cosmos that modern science paints. The standard model of cosmology fits the data beautifully, predicting the pattern of the afterglow, the way galaxies are arranged, and the history of the expansion, all with remarkable accuracy. And yet, that successful model tells us that the universe is about 5% ordinary matter, the only part we truly understand, about 27% dark matter, which we detect but cannot identify, and about 68% dark energy, which we can measure but cannot explain at all. We have, in effect, written a detailed and accurate description of a universe whose main ingredients are two enormous question marks. It is one of the great humbling facts of our age that after all our progress, we have figured out that almost everything is made of things we have not figured out. And whichever of those mysterious ingredients wins out in the long run will decide nothing less than how the entire universe ends. For the sake of giving every theory its due, we should look at the serious challengers to the standard model, because not everyone accepts that the universe is dominated by invisible dark matter and dark energy, and the alternatives are worth understanding, even though most have not won out. The boldest challenge takes aim at dark matter directly. Remember that dark matter was proposed because galaxies spin too fast to be held together by their visible matter alone. But there is another way to read that same evidence. What if there is no invisible matter at all, and instead our theory of gravity is simply wrong on the enormous scales of galaxies? This is the idea behind a proposal called modified Newtonian dynamics, put forward in the early 1980s, which suggests tweaking the law of gravity so that it gets slightly stronger than expected at the very low accelerations found in the outer parts of galaxies, which would let galaxies spin fast without any need for unseen matter. The remarkable thing is that this idea works surprisingly well for individual galaxies, often predicting how they rotate with impressive accuracy using just their visible matter, which is something the dark matter picture sometimes struggles to do so cleanly. For this reason, modified gravity has a devoted group of supporters who argue it is telling us something real that the dark matter camp is missing, but it runs into serious trouble at larger scales. It has a hard time explaining how galaxies move within great clusters. It struggles to account for the detailed pattern in the afterglow of the Big Bang, and it cannot easily explain the way structure formed in the early universe, all of which the dark matter model handles naturally. There is also a striking piece of evidence that most cosmologists consider decisive: a cosmic collision, sometimes called the bullet cluster, where two galaxy clusters have smashed through each other, and careful observation shows that the bulk of the mass, traced by how it bends light, has sailed on ahead and separated from the visible gas, exactly as you would expect if most of the mass is dark matter that passes through collisions untouched and very hard to explain if gravity is simply modified. So while modified gravity remains a real and actively researched alternative and a healthy challenge that keeps the dark matter camp honest, the weight of evidence currently sits firmly with dark matter being real stuff rather than a flaw in our understanding of gravity. There have been other alternative ideas over the years, some clever and some now firmly ruled out. Early on, when the expansion of the universe was first discovered, some suggested that maybe the galaxies were not really flying apart at all, and that light simply lost energy and reddened as it traveled across vast distances, a notion sometimes called tired light, which would mimic the redshift without any real expansion. This idea has been thoroughly tested and rejected because it fails to match a whole range of observations that the expanding universe explains naturally, including the way distant exploding stars appear stretched out in time. Others have proposed that the basic constants of nature, like the strength of the forces or even the speed of light, might have changed over cosmic history, which would alter the whole story. And while this is taken seriously enough to be carefully tested, no convincing evidence for changing constants has been found so far. One genuinely mind-bending alternative idea, which sits somewhere between serious speculation and philosophy, is the suggestion that our entire universe might be the interior of a black hole. The reasoning goes that the mathematics describing the inside of a black hole has some intriguing similarities to the mathematics of an expanding universe, which has led a few physicists to wonder whether every black hole might give birth to a new universe inside itself, inaccessible from the outside, so that our own cosmos could be nested within a black hole in some larger parent universe, which in turn contains other black holes, birthing other universes, an endless nesting of cosmos within cosmos. This connects, in a way, to the cyclic and multiverse ideas we explored, offering yet another route to the conclusion that our universe might not be alone and might not be the original one at all. It is highly speculative, far from established, and very difficult to test, but it is a real idea that serious people have explored, and it captures how strange the frontier of cosmology becomes. The honest summary of all these alternatives is that the standard model, with its Big Bang, inflation, dark matter, and dark energy, remains by far the best fit to the full range of evidence, which is why it is the standard model. But it is not the only idea anyone has ever taken seriously, and the existence of thoughtful challengers is a sign of health rather than weakness, because a theory that has fended off real competitors is one we can trust more, not less. The dark matter question, in particular, is not completely closed. The nature of dark energy is wide open, and the small cracks, like the Hubble tension, leave room for surprises. Good scientists hold the standard model firmly while keeping one eye on the alternatives, ready to change their minds if the evidence shifts, which is exactly the posture that has carried cosmology from myth to measurement in a single century, and the posture that will carry it forward into whatever it discovers next. Before we get to how the universe ends, there is a question about its shape and size that turns out to be both simple to ask and genuinely strange to answer, which is, what is the actual geometry of the universe? And is it finite or infinite? We touched on the idea that space can be curved and that the universe appears to be flat. But it is worth slowing down on what that really means, because our everyday intuition fails badly here. When cosmologists say space is curved or flat, they are not talking about the shape of some object sitting inside space. They are talking about the geometry of space itself, the rules of how lines and angles and distances behave. In a flat universe, the geometry you learned in school holds true on the largest scales. Parallel lines stay parallel forever, and the angles of a giant triangle add up to exactly what you would expect. In a curved universe, those rules bend. Parallel lines might eventually meet or drift apart, and a vast triangle might have angles that add up to more or less than they should. There are three basic possibilities. Space could be positively curved, like the surface of a sphere but in three dimensions, which would make the universe finite, curving back on itself so that, in principle, traveling far enough in a straight line could bring you back to where you started, with no edge anywhere. Or space could be negatively curved, shaped like a saddle, which would tend to make it infinite and open. Or it could be flat, balanced exactly between the two. We can actually measure which one we live in by looking at the patterns in the cosmic microwave background and seeing whether the geometry has distorted them. And the answer that comes back over and over is that the universe is flat, or so close to flat that we cannot detect any curvature at all. That flatness, you will remember, is one of the puzzles that inflation was invented to explain. And here is where it gets strange, because if the universe is truly flat and the cosmological principle holds that it looks the same everywhere, then the most natural conclusion is that the universe is infinite, that space goes on without end in every direction, containing an infinite number of stars and galaxies, and by some lines of reasoning, an infinite number of everything, including somewhere out there, perhaps endless copies of the earth and of you. This is a genuinely difficult idea to hold in the mind, an actually infinite universe. And it is important to be honest that we do not know it for certain. A flat universe is consistent with being infinite, but it could also be finite if space connects up in some clever way that we cannot detect, folding back on itself like the surface of a donut, finite in size, but with no edge or boundary. We simply cannot see far enough to tell because we are stuck inside our observable bubble, and whatever lies beyond the horizon, including the overall shape and size of the whole thing, may be permanently out of reach. So, one of the most basic questions you could ask, is the universe infinite or finite, currently has the honest answer that we do not know and may never know. This also clears up another common confusion about whether the universe has an edge or a center and what it would be expanding into. The answer, in every version of the standard picture, is that there is no edge and no center, and the universe is not expanding into anything. If the universe is infinite, then it was infinite even at the Big Bang, just infinitely denser. And the expansion is simply the stretching of all that infinite space, with every point moving away from every other and no special middle. If the universe is finite but folds back on itself, then again there is no edge to fall off and no outside to expand into, just as the surface of a balloon has no edge and no center even though it grows. The question of what the universe is expanding into assumes there must be some larger, empty space surrounding it, but that assumption may simply be wrong. Space itself is the thing that is growing, and there need not be anything outside it at all. This is one of those places where the universe refuses to behave the way our intuition, shaped by life inside ordinary rooms and landscapes, insists it should. All of this connects directly to the final great question, the fate of the universe, because the geometry and the contents together determine where everything is headed. For a long time, before we knew about dark energy, the fate of the universe was thought to depend simply on how much matter it contained, on whether gravity was strong enough to eventually halt the expansion and pull everything back. A universe with enough matter would be like a ball thrown upward that slows, stops, and falls back down. A universe with too little would be like a ball thrown so hard it escapes forever. But the discovery of dark energy, that mysterious force accelerating the expansion, completely changed the picture, because now the deciding factor is not just the pull of matter, but the push of dark energy. And the long-term behavior of dark energy is something we do not fully understand. So when we ask how the universe ends, we are really asking what dark energy will do over unimaginable stretches of time. And the honest answer is that there are several possible endings, each following from a different assumption about that mysterious two-thirds of everything. So, how does it all end? Given what we currently know, the most likely fate of the universe is a slow, cold, quiet fading away that scientists call the heat death, or sometimes the big freeze, and it follows directly from the discovery that the expansion is accelerating. If dark energy keeps behaving as it appears to now, then the universe will simply go on expanding forever, faster and faster, growing ever larger, emptier, and colder, with no end and no reversal. This is not a dramatic, fiery finale. It is the opposite, a long, gradual winding down. And to picture it, you have to think on timescales so vast they make the current age of the universe, all 13.8 billion years of it, look like the first instant. Over those immense stretches, the universe slowly runs out of the ability to do anything at all. The story of that long fading unfolds in stages. Right now, we live in what is sometimes called the age of stars, when the universe is full of bright galaxies busily forming new suns. But star formation cannot last forever because it uses up the available gas, and over the next hundreds of billions to trillions of years, fewer and fewer new stars will be born, while the existing ones burn out one by one. The biggest stars die first, and the small, dim, frugal stars last the longest. But eventually, after perhaps 100 trillion years, the last star will flicker out, and the universe will go dark, lit only by the cooling embers of dead stars. After that comes a vastly longer era, populated only by stellar corpses, the dense remnants left behind, the white dwarfs and neutron stars and black holes drifting through an ever-darkening cosmos. And because the expansion is accelerating, the galaxies beyond our own local group will eventually be carried so far away, so fast, that their light can no longer reach us at all, so that any astronomers in the extremely far future would see only their own island of stars in an otherwise empty black sky, with no evidence that the rest of the universe even exists. Over almost incomprehensible spans of time after that, even the most durable structures give way. The matter that makes up dead stars and planets may itself slowly decay over timescales that dwarf everything that came before. And then, in the deepest future, the universe enters what some physicists call the black hole era, when the largest objects remaining are the black holes, which themselves are not truly permanent. As we will see when we talk about black holes in detail, they very, very slowly leak energy and shrink. Over time, spans so long they defy any meaningful comparison, until even they evaporate away into nothing but faint radiation. And once the last black hole is gone, the universe enters its final state, the dark era, an unimaginably vast, cold, empty expanse, near absolute zero, containing only a thin, ever-thinning haze of stray particles and feeble radiation, drifting apart forever, with no energy differences left anywhere to drive any process at all. This is the heat death, the state of maximum disorder, of perfect, eternal, featureless equilibrium, the universe having finally and completely run down, like a clock whose spring has fully unwound, with nothing left to ever happen again. That is the favored ending, but it is not the only one, because it depends entirely on dark energy continuing to behave as it does now, and we cannot be sure it will. If dark energy were instead to grow stronger over time, becoming a more aggressive kind of repulsion that physicists sometimes call phantom energy, then the universe would face a very different and far more violent end, called the Big Rip. In this scenario, the accelerating expansion would not just carry distant galaxies away, it would intensify without limit until it tears apart everything in a specific, calculable sequence. First, the gray clusters of galaxies would be ripped apart. Then, individual galaxies would be torn to shreds. Then, solar systems would be pulled apart as the expansion overwhelmed even the grip of a star on its planets. Then, planets and stars themselves would be shredded. And finally, in the last fraction of a second, the expansion would grow so fierce that it would rip apart atoms and even the smallest particles, dissolving the very fabric of matter. Unlike the slow fade of the heat death, the Big Rip would have an actual endpoint, a final moment billions of years from now, but finite, when the universe quite literally comes apart at the seams. Whether this happens depends on the precise nature of dark energy, which we are still working to pin down. There is a third classic possibility, though current evidence makes it unlikely, and it is, in a sense, the mirror image of the Big Bang, called the Big Crunch. If the expansion were someday to slow, stop, and reverse, perhaps because dark energy weakened or changed character, then gravity would take over again and begin pulling everything back together. The universe would start to contract, slowly at first and then faster, galaxies rushing toward one another, the cosmos heating up as everything compressed, until finally all of space and all of matter collapsed back into a single, hot, dense point, a kind of Big Bang run in reverse, a final cosmic implosion. For a long time, this was considered a real contender, an elegant and somehow satisfying symmetry, the universe being born in a bang and dying in a crunch. But the discovery that the expansion is accelerating, not slowing, has pushed the Big Crunch well out of favor, since nothing we currently see suggests the expansion will ever reverse. Still, because we understand dark energy so poorly, no honest cosmologist will rule it out entirely. And the Big Crunch is interesting for another reason, because it opens the door to a possibility that has tempted thinkers since ancient times, the idea that the end of one universe might be the beginning of another, that the cosmos might not run down once and stop, but cycle again and again forever. There is a feature of the universe so familiar that we almost never question it, and yet it is one of the deepest puzzles in all of physics, which is that time has a direction. You remember the past, but not the future. A cup falls and shatters, but shattered pieces never leap up and reassemble into a cup. You grow older, never younger. Time, in our experience, flows one way, from past to future, with an absolute, unmistakable arrow. And here is the strange thing. When you look at the actual laws of physics, the equations that govern how particles move and interact, almost all of them work exactly the same whether you run time forward or backward. At the level of individual particles, the basic rules do not care which way time goes. The way a film of two billiard balls colliding looks perfectly sensible, played in either direction. So, if the underlying laws have no preferred direction, where does the powerful one-way arrow of our experience come from? The answer, as far as we understand it, comes back to entropy, that measure of disorder we met in the story of physics and the second law of thermodynamics, which says that the total disorder of the universe always increases over time. A broken cup is more disordered than a whole one, and there are vastly more ways for things to be broken and scattered than to be neatly assembled. So disorder reliably grows, and that growth is what gives time its direction. The arrow of time in this view is really the arrow of increasing entropy. We remember the past and not the future, because the past was more ordered, and the relentless one-way increase of disorder is what distinguishes the two. This is a beautiful answer, but it only pushes the mystery one step deeper, because if entropy is always increasing, then it must have been lower in the past and lower still further back, which means the universe must have begun in an extraordinarily ordered low entropy state, and nobody knows why. Why the universe started in such a special, highly ordered condition when overwhelmingly most possible starting states would have been disordered is one of the great unsolved questions, sometimes called the past hypothesis. And it may be that the entire direction of time and our whole experience of past and future traces back to that one unexplained fact about the universe's beginning. Relativity adds an even stranger twist to all of this, because Einstein's work suggests that our intuitive picture of time, with a special, flowing present moment, the now, that separates a fixed past from an open future, may itself be an illusion. In relativity, what counts as the present moment depends on how you are moving, so that two observers moving differently can genuinely disagree about whether two distant events happen at the same time. There is no single universal now that everyone shares. This has led many physicists to favor a picture called the block universe, in which past, present, and future all exist together, equally real, as a single unchanging four-dimensional whole, with time being just another direction within it, like a dimension of space. In this view, the flow of time, the sense that the present is rushing forward, is not a feature of the universe itself, but a feature of how our consciousness experiences it, a kind of trick of the mind. The past has not vanished, and the future is not yet to be decided. In this picture, they are simply elsewhere in the block, as real as distant places we cannot currently see. Whether this is the correct way to understand time, or whether the flow of time is somehow real after all, is hotly debated, and it remains one of the genuinely unresolved questions where physics shades into philosophy. There is a final, almost dizzying puzzle that comes out of thinking about entropy and the vast future of the universe, and it is called the Boltzmann brain problem, named after the same Ludwig Boltzmann who first understood entropy. It goes like this. We have said the universe is heading toward a heat death, a vast, near eternal state of maximum disorder. But quantum theory says that even in such a state, random fluctuations will occasionally, by sheer chance, produce little pockets of order, the way randomly shuffling a deck will very rarely produce a sorted run. Given infinite time, these random fluctuations would occasionally produce almost anything, including, with fantastically tiny but non-zero probability, a fully formed conscious brain, complete with false memories of a life and the universe flickering into existence for a moment out of the chaos before dissolving again. And here is the deeply unsettling part. In an eternal universe, simple random fluctuations producing a single lonely brain would be vastly, overwhelmingly more common than the spectacularly unlikely event of fluctuating an entire ordered universe like the one we see. So, by the numbers, a randomly selected conscious observer would be far more likely to be one of these fleeting, isolated fluctuation brains than a real person in a real, ordered cosmos. This sounds absurd, and almost everyone agrees it must be wrong. But the unsettling thing is that it is genuinely hard to explain exactly why it is wrong, and the problem is taken seriously as a constraint on our theories, because any theory of the universe that predicts we should mostly be Boltzmann brains is probably a theory that has gone astray somewhere. It is a strange place for cosmology to lead, to a paradox about whether your own memories can be trusted, and it shows how the simplest questions about time and order can spiral into the most vertiginous depths. The idea of a cyclic universe, one that is born, grows, dies, and is somehow reborn, over and over without end, is ancient, appearing in various forms in old philosophies and religions long before science took it up. In modern cosmology, it has returned in several serious versions, all trying to answer a question the standard Big Bang leaves wide open, which is what, if anything, came before the beginning. The simplest cyclic idea pairs naturally with the big crunch we just met. If the universe expands, then collapses back into a hot, dense point, then perhaps that collapse does not end in a final death, but bounces, rebounding into a new Big Bang, a new universe expanding outward, which will itself someday collapse and bounce again, an endless sequence of universes, each one rising from the ashes of the last. In this picture, there is no single beginning and no final end, just an eternal rhythm of expansion and contraction, bang and crunch and bang again, stretching infinitely into the past and the future. This idea of a bounce rather than a true beginning from nothing, appears in several modern theories, and it is appealing partly because it sidesteps the awkward question of what happened at the very first instant. If the Big Bang was not the absolute start of everything but a bounce from a previous phase, then there was always a before, and the troubling moment of creation from nothing dissolves into just another transition in an eternal process. Some versions come from attempts to combine quantum physics with gravity, which hint that the infinite density point at the heart of the Big Bang might be replaced by a bounce, a moment, when a previous contracting universe reached enormous but finite density and rebounded outward. Other versions, with names drawn from ancient ideas about fire, propose that our universe is one of two vast sheets existing in higher dimensions we cannot perceive, which periodically collide, and that each collision is what we experience as a Big Bang, with the cycle repeating as the sheets draw apart and crash together again over enormous spans of time. There is a particularly elegant cyclic idea proposed by the brilliant mathematician and physicist Roger Penrose, who won a share of a Nobel Prize for his work on black holes. His proposal, which he calls conformal cyclic cosmology, takes the heat death we just described, that final, cold, empty state of maximum disorder, and makes a startling move. He argues that in the extremely far future, once all the black holes have evaporated and the universe contains nothing but radiation spread thinly across infinite space, the universe would have lost all sense of scale, because with no matter left to serve as rulers or clocks, there would be no meaningful difference between unimaginably vast and unimaginably small. And in that strange, scaleless state, he suggests, the cold, empty, infinite end of one universe becomes mathematically identical to the hot, dense, tiny beginning of the next. The heat death of one cosmos, which he calls an aeon, smoothly becomes the Big Bang of a new one, an endless succession of universes, each flowing out of the dead remains of the one before. It is a beautiful and controversial idea, and Penrose has even claimed to find faint patterns in the cosmic microwave background that might be leftover marks from a previous aeon, though most cosmologists are not convinced. All of these cyclic and bouncing models face a serious obstacle, and it is the same relentless law we keep running into, the second law of thermodynamics, the rule that disorder or entropy always increases. If the universe simply cycled through bang and crunch over and over, the disorder should pile up from one cycle to the next, so that each universe would be messier and run differently than the last, which means the cycles could not be truly identical and eternal, and tracing them backward, you would still seem to need a beginning, an original, low, disorder starting point. The cleverness of models like Penrose's lies partly in finding ways around this entropy problem, in proposing mechanisms that reset or erase the disorder between cycles. Whether any of these mechanisms actually work in the real universe is very much unsettled, and these remain speculative ideas at the frontier rather than established science. And this brings us face to face with perhaps the most vertigo inducing question in all of cosmology, the question of what came before the Big Bang, or whether that question even makes sense. According to general relativity, in its simplest reading, time itself began at the Big Bang, which would mean there was no before. That asking what happened before the Big Bang is like asking what is north of the North Pole, a question that sounds reasonable but has no answer because you have run out of the very thing, in this case time, that the question depends on. Some physicists, including Stephen Hawking, explored ideas in which the universe has no sharp beginning at all, no first moment, but instead rounds off smoothly, the way the surface of the earth has no edge, even though it is finite. In that view, there simply is no first instant to find a cause for. Other physicists, through the cyclic and bouncing models, insist there was a before, an endless chain of prior universes. The truth is that we genuinely do not know, that the very first instant of the universe and the question of what, if anything, preceded it lies in the one place where our best physics completely breaks down, and where, for now, honest science can only say that we have run out of road. But running out of road has never stopped people from imagining what might lie beyond it. And some of those imaginings have led to the strangest theory of all, the idea that our universe is just one among countless others. The idea that our universe might be just one of many, that there could be a vast or even infinite collection of other universes out there, is called the multiverse. And it is important to understand that it is not a single theory, but a whole family of very different ideas arrived at by different routes that happen to share the conclusion that our cosmos is not all there is. Some of these are fairly modest extensions of well-tested physics, while others are wild leaps. Let us walk through the main kinds, from the tamest to the most extreme. The mildest version barely deserves a dramatic name at all. If space is infinite, as a flat universe may well be, then somewhere far beyond our observable horizon, there are other regions, other bubbles of space we can never see. And in an infinite universe with matter arranged by chance, some of those distant regions would, by sheer probability, contain arrangements identical to our own, even copies of the Earth. This is just the ordinary universe taken to its logical, infinite conclusion, and it requires nothing more than that space goes on forever. The next kind comes from the theory of inflation we met earlier. Recall that in many versions of inflation, once that burst of cosmic expansion begins, it never stops everywhere at once, but keeps going in some regions while ending in others, endlessly budding off new, expanding patches, new universes, in a process called eternal inflation. Each of these bubble universes would be a self-contained cosmos, forever cut off from the others by the inflating space between them. And here is the provocative part, because in this picture, the laws of physics, the strengths of the forces, even the number of dimensions, might come out differently in each bubble, settling into different values as each one forms. So There could be an unimaginable number of bubble universes, each with its own physics, most of them utterly different from ours, scattered through an eternally inflating sea we can never reach or observe. Our universe, with its particular laws, would be just one bubble among countless others. Then there is the multiverse that comes from quantum mechanics itself, the many worlds idea we met in the story of physics. Recall that quantum theory describes particles as existing in a blur of possibilities until they are measured, at which point a single outcome appears. The many worlds interpretation takes the mathematics completely literally and says the other outcomes do not vanish, but each one happens in its own newly separated branch of reality. Every quantum event, constantly, everywhere, splits the universe into multiple versions, one for each possible result, all equally real, branching off from one another forever. If this is right, there are countless parallel realities, growing in number every instant, in which every possible outcome of every quantum event plays out. There's also a multiverse that emerges from string theory, our leading candidate for a deeper theory of physics, because the mathematics of string theory appears to allow an enormous number of different possible universes, each with its own laws, a vast landscape of possibilities so large the numbers are almost meaningless, and some physicists argue that all of them might be realized somewhere. Why do serious scientists take any of this seriously rather than dismissing it as fantasy? The main reason is a genuine puzzle called fine tuning. When physicists examine the basic constants of nature, the precise strengths of the forces, the masses of the particles, the amount of dark energy, they find something unsettling. Many of these numbers appear to be balanced on a knife edge, tuned with extraordinary precision to values that allow a complex universe with stars and chemistry and ultimately life to exist at all. Nudge several of them even slightly, and you get a dead universe, one that collapses instantly, or flies apart before anything can form, or never makes the elements that living things require. Our universe seems suspiciously well suited to producing complexity, and that demands an explanation. One possible answer is the multiverse combined with a piece of reasoning called the anthropic principle. If there are countless universes with different laws, then most of them are sterile and lifeless. But the few, by chance, have the right settings for complexity, and of course, we find ourselves in one of those rare, life-friendly universes because we could not possibly exist in any of the others. We observe a finely tuned universe, not because someone tuned it, but because we could only ever arise in one that happened to be tuned that way, the way a puddle might marvel at how perfectly its whole fits it. But the multiverse, in all its forms, runs into a deep and troubling problem, one that goes to the heart of what science even is. By their very nature, these other universes are, in most versions, completely beyond our reach, forever cut off impossible to see, visit, or detect. And if we can never observe them, can never run an experiment that would confirm or rule out their existence, then in what sense is the multiverse a scientific theory at all, rather than a piece of philosophy or even faith? Some respected physicists argue forcefully that the multiverse, however appealing, crosses a line, that a claim which cannot in principle be tested does not belong in science. Others respond that the multiverse is not invented out of thin air, but falls out of theories like inflation and string theory that we have other reasons to take seriously, so that even if we cannot observe the other universes directly, their existence might be an unavoidable consequence of physics we can test. This is a live and genuine debate, not a settled question, and it sits right at the blurry, fascinating border between physics and philosophy. The honest position is that the multiverse is a serious idea, motivated by real puzzles and real theories that may also turn out to be permanently untestable, and reasonable scientists disagree about what to make of that. Underneath all of these cosmic theories sits a deeper problem that we have circled several times. The fact that our two greatest theories of physics do not agree with each other, and that until they are reconciled, our understanding of the universe at its most extreme will remain incomplete. On one side is general relativity, Einstein's theory of gravity, space, and time, which governs the very large, the stars, galaxies, and the universe as a whole. On the other is quantum mechanics, which governs the very small, the particles and forces inside atoms. Each is fantastically successful in its own domain, and each has passed every test we have thrown at it. But when you try to use them together in the rare places where something is both extremely heavy and extremely small, the center of a black hole, or the very first instant of the Big Bang, the mathematics falls apart and produces nonsense, infinities where there should be answers. This tells us that neither theory is the final word, that there must be a deeper theory underneath, one that contains both and works even where they fail, a theory of quantum gravity, sometimes grandly called a theory of everything. Finding it is widely considered the greatest unsolved problem in all of physics, and several candidates are being pursued. The most famous candidate is string theory, which proposes that the basic building blocks of reality are not tiny points, as we usually imagine particles, but unimaginably small vibrating strings. With the different ways a string can vibrate, giving rise to the different particles, the way one guitar string can play many notes. It is a beautiful idea, mathematically rich, and it naturally includes gravity, which is a major point in its favor. But it comes with strange requirements, including extra dimensions of space beyond the three we experience, curled up too small to see. And after decades of intense work, it has not yet made a single prediction we can actually test in an experiment, which leaves it in an uncomfortable position, a gorgeous mathematical structure that may or may not describe reality. A rival approach, loop quantum gravity, takes a different path, suggesting that space itself is not smooth and continuous, but comes in tiny, indivisible chunks, that there is a smallest possible unit of space, so that the smooth space we experience is really a fine-grained mosaic, like a photograph that looks continuous until you zoom in and see the pixels. Both of these are serious, deeply worked out attempts, and neither has yet won, and it is entirely possible the real answer is something nobody has thought of yet. Out of this struggle has come one of the strangest and most profound ideas in modern physics, the holographic principle. It emerged partly from the study of black holes, where physicists discovered something bizarre, that the amount of information you can pack into a region of space seems to depend not on its volume, as you would expect, but on its surface area, on the size of the boundary around it. This led to a startling suggestion that all the three-dimensional richness of a region of space, everything happening inside it, might be completely encoded on its two-dimensional boundary, like a hologram, those flat surfaces that store a full three-dimensional image. Taken to its extreme, the holographic principle hints that our entire three-dimensional universe, with all its depth and solidity, might be, in some deep mathematical sense, equivalent to information written on a distant two-dimensional surface, that the space we move through could be a kind of projection. This sounds like science fiction, and yet it has become a genuinely useful tool in theoretical physics because in certain model universes, physicists have shown a precise mathematical equivalence between a three-dimensional world with gravity and a two-dimensional world without it. Whether our real universe is truly holographic in this way is unknown, but the principle is taken very seriously, and it suggests that space and even gravity might not be basic features of reality at all, but might emerge from something deeper, from pure information. And once you start thinking about the universe as being made at the bottom of information, you arrive at the most modern and most science fiction sounding idea of all, the simulation hypothesis, the suggestion that our entire universe might be a kind of computer simulation run on some vast machine in another reality. The argument for taking it seriously, made carefully by a philosopher, goes roughly like this. If it is possible for an advanced civilization to build computers powerful enough to simulate conscious beings, and if such civilizations would be likely to run many such simulations, perhaps studying their own history or simply for entertainment, then there would be far more simulated realities than real ones, and so, purely by the numbers, a randomly chosen conscious being would be far more likely to be living in a simulation than in the one true base reality. It is a genuinely clever argument, and it is impossible to definitively rule out, which is exactly what makes it so unsettling. But it sits at the very edge of what could ever be called science, because it is extraordinarily hard to imagine an experiment that could truly test it, and most physicists regard it as a fascinating philosophical puzzle rather than a scientific theory. Still, it captures something real about where modern physics has wandered into a place where the solid physical universe seems to dissolve, on close inspection, into mathematics and information, and where the line between a physical reality and an abstract computation grows strangely thin. It is worth stepping back to notice just how speculative the ground has become as we have moved through these theories. We started on the rock solid foundation of the Big Bang, supported by three independent pillars of evidence. We moved to inflation, well supported but not certain. We passed through dark matter and dark energy, confirmed in their effects but utterly mysterious in their nature. We considered the fate of the universe, which depends on dark energy we do not understand. And now we have arrived at cyclic universes, multiverses, holographic reality, and cosmic simulations, ideas that range from serious frontier physics to the boundary of philosophy, most of which we currently have no way to test at all. This is not a failing. It is simply an honest map of where human knowledge runs out. The remarkable thing is how far the solid ground extends, how much we genuinely do know about the origin and contents and probable fate of the entire universe. And the equally remarkable thing is how clearly we can see the edge of that knowledge, the precise places where evidence gives way to speculation, and we must admit that we are guessing. Good cosmology is the art of knowing exactly which is which. It would be a mistake to leave you with the impression that cosmology is a finished science, a tidy story with only a few exotic details left to fill in. Because in fact, the field is in a genuinely exciting and unsettled state right now, with real cracks appearing in the standard picture that may be pointing toward new physics. The sharpest of these is something called the Hubble tension, and it concerns the most basic number in all of cosmology, the rate at which the universe is expanding. There are two main ways to measure that rate. One is to look out at the nearby universe and carefully build up distances using the cosmic distance ladder, the pulsing stars and exploding stars we met in the story of astronomy. The other is to start from the afterglow of the Big Bang, the cosmic microwave background, and use our detailed theory of the early universe to calculate what the expansion rate should be. Both methods are extremely careful, refined over years by many teams, and they should give the same answer. They do not. The two measurements disagree by a small but stubborn amount, and as the measurements have grown more and more precise instead of converging, the gap has held firm and even sharpened. This is a big deal because it means one of two things, and both are interesting. Either there is some subtle error hiding in one of the measurements that nobody has yet found, despite enormous effort, or the disagreement is real and it is telling us that something is missing from our standard model of cosmology, some new ingredient or new physics that we have not accounted for. Cosmologists have proposed all sorts of possible explanations, from new kinds of particles in the early universe to dark energy that changes over time to modifications of gravity itself. but none has clearly won out. The Hubble tension is, right now, one of the hottest unsolved problems in the field, and there is real hope among many cosmologists that it might be the thread that, when pulled, unravels part of our current picture and leads to a deeper understanding, the way small discrepancies have triggered revolutions before. And the Hubble tension is not the only place the standard picture is being tested and surprised. The newest and most powerful space telescope, peering at the most distant and earliest galaxies, has found some of them to be surprisingly large and surprisingly mature for how early they appear in cosmic history, more developed than the simplest models expected galaxies to be so soon after the Big Bang. This does not overturn the Big Bang, but it is forcing astronomers to rethink the details of how quickly the first galaxies grew, a reminder that even our well tested theories have plenty of room for surprises when we finally get to look directly at the eras they describe. Each new generation of instruments tends to find that the universe is a little stranger and a little more interesting than we assumed. Meanwhile, scientists are pushing on every front to chip away at the great mysteries. Deep underground, in laboratories shielded from interference, sensitive detectors wait patiently for the faint signal of a dark matter particle striking them, so far without a confirmed catch, narrowing down what dark matter can and cannot be. New surveys are mapping the positions of millions of galaxies across cosmic time to track precisely how dark energy has behaved over the history of the universe, hunting for any sign that it is changing, which would transform our predictions about the fate of everything. And cosmologists are searching the afterglow of the Big Bang for an extremely faint, specific pattern that would be the fingerprint of the gravitational waves predicted by inflation, a discovery that would be a powerful confirmation of that theory and a direct glimpse of the universe's very first instant. Each of these efforts is a genuine attempt to convert one of the great unknowns into something measured and understood, and any one of them could deliver the next breakthrough. So the picture you should carry away is not of a closed book, but of a science very much in motion, with a solid, well-tested core and a turbulent, exciting frontier where the next discoveries are brewing. The Big Bang stands firm, but the value of its own expansion rate is in dispute. The standard model fits the data beautifully, yet it is built on two vast mysteries and is showing small cracks that might lead somewhere new. The early galaxies are surprising us. The dark sector refuses to give up its secrets, and the deepest questions about the beginning, the fate, and the possibility of other universes remain wide open. This is what a healthy science looks like. Not a list of final answers, but a living argument, full of hard-won knowledge and honest uncertainty, where the people doing the work are genuinely unsure how some of the biggest questions will turn out, and that uncertainty, far from being a weakness, is exactly what makes this the most exciting time to be paying attention to the universe. It is worth dwelling longer on the afterglow of the Big Bang, the cosmic microwave background, because it is by far our richest source of information about the universe as a whole. A single, faint glow that, read carefully, reveals the age, the composition, the geometry, and the history of the entire cosmos with astonishing precision. Recall that this afterglow was released when the universe was only a few 100,000 years old, the moment it cooled enough to become transparent, and that it now reaches us from every direction as a faint hiss of microwaves, cold radiation just a few degrees above absolute zero. At first, it seemed perfectly smooth, the same temperature everywhere, but cosmologists realized that hidden in it must be tiny variations, slight differences in temperature from place to place, the imprints of the slightly denser and slightly emptier regions that would eventually grow into galaxies and voids. Finding and mapping those variations became one of the great quests of modern cosmology. A series of increasingly sophisticated space telescopes was sent up to map this afterglow in ever finer detail, and each one transformed our knowledge of the universe. The first detected the long sought variations, revealing that the afterglow is indeed not perfectly smooth, but marked by faint ripples, differences of about 1 part in 100,000, the seeds of all the structure that exists, a discovery so important it earned a Nobel Prize. Later, missions mapped these ripples across the whole sky in exquisite detail, producing the famous modeled images of the infant universe that you may have seen. A baby picture of the cosmos showing the slight temperature differences as patches of color, the oldest light there is, frozen as it was when the universe was young. These maps are among the most information-rich images ever made, because the precise pattern and size of those ripples encodes an enormous amount about the universe. Here is the remarkable thing, that the detailed statistics of those tiny ripples, exactly how much variation there is at each size scale, act as a kind of fingerprint that lets cosmologists read off the basic properties of the entire universe. By analyzing the pattern of the ripples, cosmologists can determine the age of the universe, which is how we know it to be about 13.8 billion years old, with such confidence, and they can measure the overall geometry of space, which is how we know it is flat to high precision, and they can weigh the universe, determining how much of it is ordinary matter, how much is dark matter, and how much is dark energy, which is the source of those precise percentages we have quoted. An astonishing amount of what we confidently claim to know about the universe as a whole comes from this single source, the careful analysis of the faint afterglow of the beginning, which acts as a cosmic Rosetta Stone, translating the conditions of the early universe into hard numbers. The way the ripples encode all this is genuinely beautiful, and it comes down to sound. In the hot, dense, early universe, before the afterglow was released, the mixture of matter and radiation behaved like a fluid, and the slight, overdense regions set up pressure waves, in effect, sound waves, that rippled through the early cosmos. When the universe became transparent and released the afterglow, these sound waves were frozen into the pattern, leaving a characteristic scale, a particular size that shows up preferentially in the ripples, like a note ringing at a specific pitch. The size of that frozen sound, both as we see it imprinted in the afterglow and as it appears in the way galaxies are spaced across the sky today, gives cosmologists a kind of standard ruler, a known length they can use to measure distances and the expansion of the universe across cosmic time. The infant universe was, in a real sense, ringing like a bell, and the echoes of that ringing, captured in the afterglow and in the arrangement of galaxies, are one of the most powerful tools we have for measuring the cosmos. All of this is why cosmology, once a field of grand speculation with little hard data, has in recent decades become a precision science, with the basic properties of the universe pinned down to a few percent. It is genuinely astonishing that we can speak with such confidence about the age and composition and shape of the entire universe, and that confidence rests, more than on anything else, on the exquisite measurements of this faint afterglow of creation. The cosmic microwave background is, in effect, the anchor of the whole standard model of cosmology, the observation against which our theories are tested and from which our key numbers are drawn, and the fact that the detailed predictions of the Big Bang model match the intricate pattern of the afterglow so precisely is one of the strongest reasons we trust the whole picture. When you hold in mind that this faint glow has been traveling toward us unimpeded for over 13 billion years, carrying within its subtle ripples the blueprint of everything that would later form, it becomes one of the most precious and remarkable signals in all of science, the universe's own record of its infancy, waiting to be read. We met cosmic inflation earlier as the burst of staggering expansion in the first sliver of a second, but it is worth understanding more deeply why cosmologists take it so seriously, and also why it remains, for all its successes, not yet fully proven. Inflation was proposed to solve those nagging puzzles, the horizon problem of why distant regions of the sky have the same temperature when they could never have been in contact, and the flatness problem of why the geometry of space is so suspiciously close to perfectly flat. Inflation solves both elegantly by proposing that the entire visible universe grew out of a tiny patch that was small enough to have evened itself out before being stretched to enormous size, which both explains the uniformity and flattens out any curvature. On its own, solving two puzzles might not be enough to compel belief, but inflation does something more impressive. It makes a specific, detailed prediction that we can check. That prediction concerns those tiny ripples in the afterglow we just discussed. Inflation says that before the great expansion, the tiny patch that became our universe would have had unavoidable quantum fluctuations in it. The tiny, random jitter that quantum mechanics says is always present, even in empty space. The sudden, enormous stretching of inflation would have taken those microscopic quantum fluctuations and blown them up to astronomical size, freezing them into the fabric of the cosmos as slight variations in density, the very seeds that would grow into galaxies. So inflation predicts not just that there should be ripples, but a specific pattern to them, a particular way the variation should be distributed across different sizes. And when cosmologists measured the actual ripples in the afterglow, the pattern matched the prediction of inflation remarkably well. This is the strongest evidence for inflation, that a theory about the first tiny fraction of a second makes a detailed prediction about the pattern of the oldest light in the universe, and the prediction comes true. There is an even more dramatic prediction that cosmologists have been hunting for, which would, if found, be considered a smoking gun for inflation. And the search for it is one of the great quests of modern cosmology. The theory predicts that the violence of inflation should have produced not only ripples in density, but also gravitational waves, ripples in the fabric of space-time itself, echoing from that first instant. These primordial gravitational waves would be far too faint to detect directly, but they should leave a faint, distinctive swirling pattern imprinted in the way the afterglow's light is polarized. A subtle twist that inflation and almost nothing else could produce. Detecting that swirl would be a direct glimpse of the universe's very first moment and powerful confirmation of inflation. And so teams of cosmologists have built sensitive instruments to search for it. This search also produced a famous cautionary tale, a reminder of how science is supposed to work and of how easy it is to be fooled. In the year 2014, one team announced to great excitement that they had detected exactly this swirling signature, the fingerprint of primordial gravitational waves from inflation, and for a few weeks it was hailed as a monumental discovery. But as other scientists scrutinized the result, it emerged that the signal could be explained not by primordial gravitational waves at all, but by ordinary dust in our own galaxy, which can produce a similar swirl, and the claimed discovery had to be withdrawn. It was a disappointment, but also a healthy example of science correcting itself, of an extraordinary claim being checked, found wanting, and retracted, rather than being accepted on authority. The search for the true signal continues with ever more sensitive instruments, and finding it remains one of the great prizes of cosmology, a direct window onto the first instant of creation. So, inflation sits in an interesting place, far more than a wild guess, but not quite a settled certainty. It is widely accepted because it elegantly solves real problems and because its prediction about the pattern of the ripples in the afterglow has been confirmed, and most cosmologists regard some form of it as very likely true. And yet, we still do not know what actually drove inflation, what kind of energy field powered that burst of expansion. And there are many different versions of the theory making slightly different predictions. With the decisive direct evidence, the swirl in the afterglow not yet found, there is also that strange and profound implication we noted, that in many versions of the theory, inflation never fully stops everywhere, but keeps going in some regions while ending in others, endlessly spawning new universes, which would mean our cosmos is just one bubble in an eternally inflating sea. Inflation, in other words, is a powerful and well supported idea that nonetheless still trails deep uncertainties and points toward possibilities, like the multiverse, that may lie forever beyond our ability to test, which makes it a perfect example of cosmology at the edge of what we can know. To understand the very first moments of the universe and some of the deepest theories about it, we need to talk about the forces of nature, because the story of the early universe is in large part the story of those forces separating out as everything cooled. As we saw in the story of physics, everything that happens in the universe is governed by just four basic forces. There is gravity, which shapes the cosmos on the largest scales. There is electromagnetism, responsible for light, electricity, and the behavior of atoms. And there are two forces that act only within the atomic nucleus: the strong force that binds the nucleus together, and the weak force responsible for certain kinds of radioactive decay. These four forces, with their wildly different strengths and ranges, govern everything, and the central dream of physics has been to show that they are, deep down, different faces of a single underlying force. The reason this dream connects to cosmology is that the strength and even the separateness of the forces depend on energy and temperature, and the early universe was unimaginably hot. The leading idea is that at the colossal temperatures of the first instance, the forces were not separate at all, but unified, merged into one or a few, and that as the universe expanded and cooled, they split apart one by one, freezing out into the distinct forces we know today, like steam condensing into water and then freezing into ice as it cools. Physicists have actually confirmed part of this picture, having shown that at high enough energies, the electromagnetic force and the weak nuclear force merge into a single electroweak force, a unification confirmed when the particles it predicted were discovered in the laboratory. So we know for certain that at least two of the four forces were once one, which strongly suggests the others may have been two. This leads to the grand theories that try to extend the unification further, the so-called grand unified theories, which propose that at even higher energies, found only in the first tiny fraction of a second after the Big Bang, the strong force would also merge with the electroweak force, leaving just gravity standing apart. And the ultimate dream, the theory of everything, would unite even gravity with the other three, showing that all four forces are different aspects of a single original force that ruled the first instant of creation, before the universe cooled enough for them to separate. The grand unified theories remain unproven, and the full theory of everything that includes gravity is exactly the quantum gravity we keep searching for and have not found. But the picture they paint is compelling, of a universe that began in perfect simplicity, a single unified force, and grew more complex and varied as it cooled, the rich diversity of nature emerging from an original unity through a series of symmetry breakings. Running the clock all the way back, we reach the genuine edge of physics, the very first sliver of time, often called the Planck epoch, lasting an almost inconceivably tiny fraction of the first second. During this earliest instant, the universe was so hot and so dense that all four forces, including gravity, were likely merged into one, and the energies were so extreme that we would need a complete theory of quantum gravity to describe what was happening, a theory we do not possess. So the Planck epoch is, quite literally, beyond our current physics, a curtain we cannot see behind, the one stretch of cosmic history where our equations simply give out. Everything we have said about the universe's evolution, the inflation, the cooling, the formation of particles and elements, begins after this curtain, in the first tiny fractions of a second that we can describe. What happened in that very first instant, and what, if anything, set the whole thing going, remains the deepest unanswered question in all of cosmology. There is one more profound puzzle from the early universe worth recalling here, because it touches on why anything exists at all, and that is the matter-antimatter problem we explored earlier. The hot early universe should have produced matter and antimatter in equal amounts, which would have annihilated completely, leaving a universe of nothing but light. Instead, a tiny imbalance, about one extra particle of matter for every billion pairs, survived the great annihilation, and that minuscule leftover is everything we see, every star and planet and person. Why there was that slight excess of matter over antimatter is still not fully understood, and it is connected to the deep physics of the forces and particles in the early universe. One more way that the story of the cosmos and the story of the smallest particles are intertwined. The early universe, in other words, is where cosmology and particle physics meet, where the largest questions about the universe as a whole depend on the deepest questions about the forces and particles that make it up, and where many of the greatest unsolved problems in all of science are concentrated, waiting at the very beginning of time. Dark matter deserves a closer look because it is one of the strangest situations in all of science, a substance that makes up most of the matter in the universe, and that we are certain exists, yet have never directly seen or identified. The evidence for it comes from many independent directions, all pointing the same way, which is why cosmologists are so confident it is real, despite never having caught a particle of it. The first hint came back in the 1930s, when an astronomer studying a cluster of galaxies found that the galaxies were moving far too fast to be held together by the gravity of the visible matter alone, as if there were a great deal of unseen mass holding the cluster together. Decades later, the astronomer Vera Rubin found the same thing within individual galaxies, that the stars at their edges orbit far too quickly for the visible matter to hold them, requiring vast halos of invisible matter. Since then, the evidence has only mounted from the way invisible mass bends light to the very pattern of the afterglow of the Big Bang, to the way galaxies and large structures formed at all. Every line of evidence pointing to the same conclusion that there is far more matter than we can see. A particularly striking piece of evidence comes from a cosmic collision where two great clusters of galaxies have crashed through each other, and which is often considered close to a direct proof of dark matter. When astronomers studied this collision, they could map separately where the ordinary visible matter was, mostly hot gas, and where the bulk of the mass was, traced by how it bent light. And they found that the two had separated, with most of the mass having sailed straight through the collision and moved on ahead, while the ordinary gas was left behind, slowed by the crash. This is exactly what you would expect if most of the mass is dark matter that passes through collisions almost untouched and very hard to explain any other way, which is why most cosmologists regard it as compelling evidence that dark matter is real stuff, not merely a mistake in our understanding of gravity. Despite all this evidence that dark matter exists, the question of what it actually is remains completely open, one of the great unsolved mysteries. We know it is not made of ordinary atoms, because ordinary matter is accounted for separately, and there is far too little of it, and we know it does not give off, absorb, or block light, which is why it is dark and invisible, betraying itself only through gravity. The leading idea for many years was that it consists of some new kind of particle, not yet discovered, left over from the early universe, a particle that barely interacts with ordinary matter at all, passing through it and through us like a ghost. Various candidate particles have been proposed, with names and properties suggested by different theories, and enormous, painstaking experiments have been built to try to catch one deep underground to shield them from interference, waiting for the incredibly rare event of a dark matter particle bumping into ordinary matter. So far, despite decades of searching, none has been caught, and the leading candidate particles have not shown up where they were expected, which has deepened the mystery and sent physicists looking at other possibilities. The alternatives are themselves fascinating. Some physicists wonder whether dark matter might be made of black holes formed in the early universe rather than of any new particle, while others, as we discussed, question whether dark matter exists at all and propose instead that our theory of gravity is simply wrong on the scales of galaxies, an idea that elegantly explains some observations but struggles with others, especially that cosmic collision and the afterglow of the Big Bang. The honest situation is that the existence of dark matter is established beyond reasonable doubt by its gravitational effects, while its actual nature remains one of the most important unanswered questions in physics, with the leading explanations stubbornly failing to confirm themselves in the laboratory. It is a humbling state of affairs that the most common kind of matter in the universe, the stuff that outweighs everything we can see by 5 to 1 and that built the scaffolding on which all the galaxies hang, is something we cannot identify, name, or detect except by the pull of its gravity. This matters enormously for the whole picture of the universe, because dark matter is not some minor exotic addition but the dominant form of matter the gravitational backbone of the cosmos, without which galaxies and the great cosmic web could not have formed as they did. Our entire standard model of cosmology, which fits the data so beautifully, depends on dark matter being there, providing most of the gravity that shaped the universe's structure. So we are in the strange position of having a successful, precise theory of the cosmos that is built in large part on a substance we have never identified, a profound clue that there is new physics waiting to be discovered, some new particle or new understanding that, when found, will fill in one of the largest blanks in our knowledge of what the universe is actually made of. The search for dark matter is, in a real sense, a search for the missing majority of the material universe, and finding it would be one of the great discoveries in the history of science, while continuing to fail to find it may eventually force an even more radical rethinking of physics itself. If dark matter is mysterious, dark energy is stranger still, the largest single component of the universe and the one we understand least, and its discovery is one of the great surprises in the history of science. The story begins in the late 1990s when two independent teams of astronomers set out to measure how the expansion of the universe was slowing down. Everyone expected it to be slowing because the combined gravity of all the matter in the cosmos should be pulling everything back together, gradually putting the brakes on the expansion that began with the Big Bang. The teams used distant exploding stars, the reliable standard candles we met in the story of astronomy, to measure the expansion rate far back in time and compare it to today, expecting to find the expansion decelerating. Instead, both teams found, to their astonishment and initial disbelief, the opposite. The expansion of the universe is not slowing down at all. It is speeding up. Something is pushing the universe apart, faster and faster, overwhelming the inward pull of all the matter. And that discovery, which earned the Nobel Prize, upended cosmology and revealed that most of the universe is made of something nobody had expected. That something was named dark energy, and the name, like dark matter, is really a label for our ignorance, a placeholder for whatever is causing the accelerating expansion. The leading idea is that it is a kind of energy belonging to empty space itself, a property of the vacuum, so that as the universe expands and there is more space, there is more of this energy driving the expansion ever faster. This connects to an idea Einstein had introduced and then abandoned, a term in his equations representing a constant energy of space, which he had called his greatest blunder, and which came roaring back as possibly the dominant feature of the entire cosmos, now usually called the cosmological constant. If dark energy is indeed this constant energy of the vacuum, then it has been there all along and will drive the expansion to accelerate forever, leading to the cold, empty fate we discussed. There is a profound and embarrassing problem at the heart of this, however, one of the deepest in all of physics. If dark energy is the energy of empty space, then quantum physics ought to be able to calculate how much energy of empty space should contain, since the quantum vacuum is not truly empty but seething with activity. When physicists attempt that calculation, they get a number that is larger than the amount we actually observe, by a factor so vast it is almost beyond comprehension, a number with about 120 zeros after it. This is sometimes called the worst prediction in the history of physics, the most spectacular disagreement between theory and observation ever. And it means that while we can measure the effect of dark energy with precision, our attempt to explain what it actually is produces nonsense off by a margin so enormous it signals that something is deeply wrong or missing in our understanding. The nature of dark energy is, in other words, not just unknown, but genuinely baffling, a sign that we are missing something profound about the vacuum, about gravity, or about both. Because of this, physicists have proposed alternatives to the simple cosmological constant ideas in which dark energy is not a fixed property of space, but something more dynamic, a field that can change in strength over cosmic time, sometimes given names suggesting a fifth essence beyond ordinary matter and energy. The crucial difference is that a changing dark energy would have a different effect on the universe's history and fate than a constant one, and so cosmologists have been working hard to measure, with ever greater precision, whether the strength of dark energy has stayed constant or has changed over the history of the cosmos. This is not merely an abstract question, because the answer determines nothing less than the ultimate fate of the universe, whether it fades into a slow, cold heat death, tears itself apart in a big rip, or does something else entirely, all hinging on the behavior of this mysterious energy we cannot explain. And here is a genuinely exciting recent development that shows cosmology is very much a living science, because some of the latest and most precise measurements of how the universe has expanded over time have produced tantalizing hints that dark energy might not be constant after all, that it may have been changing over cosmic history. These results are not yet conclusive, and cosmologists are appropriately cautious, because extraordinary claims require extraordinary evidence, and the measurements are at the very edge of what we can detect. But if these hints hold up under further scrutiny, they would be revolutionary, overturning the simple picture of dark energy as a constant and forcing a deep rethinking of the fate of the universe and of basic physics. It is a perfect illustration of how unsettled and alive cosmology remains, that the largest component of the universe, making up roughly two-thirds of everything, is something we discovered only recently, cannot explain, and are not even sure is constant, with new data right now potentially upending what we thought we knew. Dark energy stands as the deepest mystery in cosmology, the vast unknown that dominates the universe and that holds the key to how everything ends, and unraveling it may require or reveal a revolution in our understanding as profound as any in the history of science. Underneath all the theories about the universe lies a question so deep that it is easy to overlook, which is what space and time actually are. And the more closely we examine it, the stranger the answer becomes, leading to some of the most radical ideas in modern physics. For most of history, space and time were taken to be the fixed, unchanging stage on which everything happens, an empty container in which events play out, and time a steady, universal flow. Einstein shattered that comfortable picture, as we saw, revealing that space and time are woven together into a single, flexible fabric. Space-time that bends and stretches in response to matter and energy, that can be warped by gravity and dilated by motion. In Einstein's universe, space and time are not the fixed backdrop, but active participants, dynamic and malleable. And this was already a profound revolution in how we understand the most basic features of reality. But Einstein's spacetime, for all its flexibility, is still smooth and continuous. And here it collides with quantum mechanics, which suggests that at the very smallest scales, everything should be grainy, jittery, and uncertain. When physicists try to combine the two, to ask what spacetime is like at the tiniest scales, the smooth fabric of Einstein's theory and the jittery quantum world refuse to fit together, and the mathematics breaks down. This is the same deep incompatibility we have met again and again, the failure to unite general relativity and quantum mechanics into a single theory of quantum gravity, and it means that we do not actually know what space and time are at their most basic level. The two great candidate theories take very different views. One, string theory, suggests that the basic constituents of reality are tiny vibrating strings and requires extra dimensions of space beyond the three we experience, curled up too small to see. The other, loop quantum gravity, proposes that space itself is not smooth and continuous, but comes in tiny, indivisible chunks, so that there is a smallest possible unit of space, a graininess to reality far below anything we can currently detect. The most radical and exciting idea to emerge from these struggles is the suggestion that space and time might not be basic features of reality at all, but might emerge from something deeper. The way the smoothness of water emerges from the motion of countless individual molecules. On this view, spacetime would not be the core stage, but a kind of large-scale appearance, arising from some more basic underlying reality that is not itself spatial or temporal in the ordinary sense. And the deepest versions of this idea connect spacetime to information and to the strange quantum link of entanglement, suggesting, astonishingly, that the very fabric of space might be woven out of the entanglement between quantum systems, that the connections holding space together are, at bottom, the quantum correlations we explored in the story of physics. If this is right, then space and time are not the bedrock of reality, but emergent phenomena, and the true foundation of the universe is something stranger, made of information and entanglement, from which space, time, and gravity all somehow arise. These ideas connect back to the holographic principle we discussed, the startling suggestion that all the three-dimensional richness of a region of space might be encoded on its two-dimensional boundary, like a hologram, taken together with the idea of emergent space-time. This paints a picture of reality utterly unlike our everyday intuition, in which the solid, three-dimensional world of space and time that we inhabit might be a kind of projection or large-scale appearance arising from a deeper level of reality that is lower dimensional, made of information, and woven together by quantum entanglement. This is among the most active and exciting frontiers in all of theoretical physics, where the deepest questions about the universe, about quantum gravity, about black holes, and about the nature of space and time all converge, and where many physicists believe the next great revolution in our understanding will come. It is genuinely humbling that, after all our progress, we do not actually know what the two most basic features of our experience, space and time, truly are. What makes all of this more than idle speculation is that black holes, which we explore in their own right elsewhere, have become a kind of laboratory for these ideas, because it is at the edge of a black hole and at the singularity within it that space and time are pushed to their most extreme, where quantum gravity must take over, and where the puzzles about information and the nature of space-time become sharpest. The deep connections being discovered between the physics of black holes, the holographic principle, quantum entanglement, and the possible emergence of space-time have made this one of the most fertile areas of physics, even though it remains far from any complete answer. The upshot is that the deepest theory about our universe may turn out to be not a theory about things moving through space and time, but a theory of how space and time themselves come to exist. A theory in which the stage and the players, the container and the contents, the geometry of the cosmos and the matter within it all emerge together from some deeper reality we are only beginning to glimpse. We set out to understand the universe, and we have ended up questioning whether even space and time, the most basic features of all, are really deep, which is perhaps the most profound place that the theories about our universe have led us. Having gone deeper into the theories and the evidence, it is worth pausing on the very deepest questions of all, the ones that sit at the outer limit of what cosmology can address, and on the genuine limits of what we will ever be able to know. The largest question, the one underneath everything, is why there is something rather than nothing, why there is a universe at all rather than just empty, eternal nothingness. Even if we trace the cosmos all the way back to the Big Bang, even if we one day understand inflation and quantum gravity and the very first instant completely, we are still left facing the bare fact of existence itself. The question of why anything exists for the laws of physics to act upon. Some physicists argue that science can chip away at this, pointing to how the quantum vacuum is never truly empty and how a universe might in some sense arise from such a state, but the objection always lands that a quantum vacuum with laws is already something, not nothing, so these ideas may push the question back without ever fully answering it. It may be that this is the one question no theory can ever close, the bedrock mystery beneath all the others. A closely related puzzle is the fine tuning of the universe, the unsettling observation that many of the basic constants of nature appear to be balanced on a knife edge, tuned with extraordinary precision to values that allow a complex universe with stars, chemistry, and ultimately life to exist at all. Nudge several of these numbers even slightly, and you get a dead universe, one that collapses instantly or flies apart before anything can form or never makes the elements life requires. Why the universe should be so suited to producing complexity is a genuine puzzle, and the proposed answers range from the idea that there is some deeper principle we have not found that fixes the constants to the multiverse combined with the observation that we could only ever find ourselves in a universe capable of producing us, to the possibility that it is simply an unexplained fact. None of these is established, and the fine tuning of the universe remains one of the most debated and profound questions in cosmology, sitting right at the blurry border between physics and philosophy. There is also a remarkable and humbling limit on what we can ever observe, which flows directly from the accelerating expansion driven by dark energy. Because that expansion is carrying distant galaxies away from us faster and faster, there will come a time in the far future when all the galaxies beyond our own local group will have receded so far and so fast that their light can no longer reach us at all, vanishing forever beyond our horizon. Far future astronomers living in that distant epoch would look out and see only their own island of stars in an otherwise empty black sky, with no other galaxies visible, no afterglow detectable, no sign that the rest of the universe even exists. They would have no way to discover that the universe is expanding, no way to deduce the Big Bang, no way to learn the true nature of the cosmos, because the very evidence we rely on would have disappeared beyond reach. This is a genuinely sobering thought, that we happen to live at a privileged moment in cosmic history, late enough that the universe has produced stars and planets and us, but early enough that the evidence of its true nature is still visible. The cosmos is, in a real sense, slowly erasing the clues to its own history, and we are fortunate to be looking while they remain. This points to a deeper humility at the heart of cosmology, the recognition that there are hard limits on what we can know about the universe, and that we must be honest about them. We can only ever see the observable universe, the part whose light has had time to reach us, and what lies beyond that horizon, including the overall size and shape and fate of the whole, may be permanently beyond our reach. The very first instant of the universe lies behind a curtain our physics cannot yet penetrate. The other universes of the multiverse, if they exist, are by their nature unobservable, and the future will hide more than the present reveals. Good cosmology, as we have seen throughout, is the art of knowing exactly which of our claims are solidly established, which are reasonable inferences, which are speculation, and which lie forever beyond the possibility of knowing and of being honest about each. The willingness to say we do not know, and even we can never know, is not a weakness of the science, but a mark of its maturity. And yet, for all these limits, the sheer scope of what we have managed to learn remains staggering, and cosmology continues to advance at a remarkable pace, with new instruments and new ideas constantly pushing back the frontier of the knowable. We have measured the age and composition and shape of the entire universe, traced its history back to its first minutes, weighed its invisible ingredients, sketched its possible fates, and probed questions about space, time, and existence itself that were once thought forever beyond the reach of science. We have done all of this from a single small planet in barely a century of serious effort, and the work goes on, with deep puzzles wide open and new discoveries arriving all the time. The universe has turned out to be far stranger, far larger, and far more mysterious than anyone imagined, and the deeper we look, the more the solid ground of certainty gives way to genuine, open questions. That, in the end, is what makes cosmology so endlessly compelling. This combination of staggering knowledge and profound mystery, of hard won answers and questions we may never resolve, all in the service of understanding the single largest thing there is, the universe that contains us and everything we have ever known. We sketched the heat death of the universe earlier, but the full story of the far future, of how the cosmos slowly winds down over spans of time that beggar the imagination, is one of the most extraordinary things science has ever worked out, and it deserves to be told in more detail. Cosmologists who have studied the deep future divide it into a series of vast eras, each one almost incomprehensibly longer than the last, and we are living in only the first of them, the age of stars, when the universe is full of bright galaxies busily forming new suns. This stelliferous era, lovely as it is a passing phase, a brief flowering early in the universe's life, and it cannot last because star formation depends on a supply of gas that is steadily being used up and not fully replenished. Over the next hundreds of billions to trillions of years, the universe will slowly run out of the gas it needs to make new stars, and the existing stars will burn out one by one. The largest, brightest stars die first, in spans of mere millions of years, while the smallest, dimmest red dwarfs, sipping their fuel frugally, will shine on for trillions of years, far longer than the current age of the universe. But eventually, after perhaps 100 trillion years, even the longest lived stars will flicker out and the universe will enter a new phase, the degenerate era, a vast, dark stretch, lit only by the cooling embers of dead stars, the white dwarfs and neutron stars, and by the rare flashes of collisions. The galaxies will still be there, but dark, populated by stellar corpses drifting in the deepening gloom, no longer the bright pinwheels of the age of stars, but graveyards of burned out suns. The degenerate era may last for a span of time so long it is almost meaningless to state, and during it, the very matter that makes up those stellar remnants may slowly dissolve. Some theories of physics predict that the proton, one of the basic building blocks of all ordinary matter, is not perfectly stable but will very slowly decay over timescales so vast they dwarf everything that came before, perhaps far longer than a trillion years. If protons do decay, then over those unimaginable spans, the dead stars and planets, and all ordinary matter will gradually evaporate away, their atoms dissolving particle by particle, until the degenerate era ends with the last of the ordinary matter gone, leaving behind only the most extreme objects of all, the black holes. Whether protons truly decay is not yet known, one more open question, but if they do, it spells the eventual end of all ordinary matter in the cosmos. After the matter is gone, the universe enters the black hole era, when the largest structures remaining are the black holes, which dominate a cosmos grown almost unimaginably old, dark, and empty. But as we explore in the story of black holes, even these are not eternal, because they very slowly leak energy and shrink through a subtle quantum process, evaporating away over time scales that make all the previous eras seem fleeting, with the largest black holes taking something like 10 to the 100th power years or more to finally disappear. That is a one followed by 100 zeros, a span of time so far beyond comprehension that the entire current age of the universe is less than an eye blink by comparison. One by one, over these almost infinite stretches, the black holes will evaporate, the smallest first and the largest last, until at last the final black hole winks out in a faint puff of radiation, and the last great structures of the cosmos are gone. And then comes the final state, the dark era, the true end of the cosmic story, an unimaginably vast, cold, empty expanse, containing only a thin, ever thinning haze of stray particles and feeble radiation, drifting apart forever in the dark, near absolute zero, with no stars, no matter, no black holes, no structure of any kind, and no energy differences left anywhere to drive any process at all. This is the heat death in its fullest form, the universe having finally and completely run down, reached maximum disorder, and settled into an eternal, featureless stillness from which nothing can ever again emerge. It is a sobering vision, the ultimate fate of everything, though it lies so unimaginably far in the future that it has no bearing on anything we will ever experience, and it depends, as we have stressed, on dark energy continuing to behave as it does now, since a different dark energy could instead bring the violent Big Rip or some other ending. There is, perhaps, a strange grandeur in being able to foresee the end of the universe at all, to trace from our brief moment near the bright beginning the whole long arc of cosmic time down to its final darkness, and to understand that we exist in the universe's youth, in the rare and precious era when stars still shine and there are minds to wonder at them. The idea of the multiverse is so striking and so often confused that it is worth laying out more carefully just how many different versions of it there are, because they come from completely different lines of reasoning and range from the nearly inevitable to the wildly speculative. One useful way to organize them, suggested by a physicist who has thought deeply about this, is to picture several levels of multiverse, each more radical than the last. The mildest level barely deserves the dramatic name because it follows simply from the universe being very large or infinite, in which case there are regions beyond our horizon that we can never see. And in an infinite universe, by sheer chance, some distant regions would contain arrangements identical to our own, even copies of the Earth and of you, not in some other dimension, but simply very far away in the same space. This requires nothing more than that space goes on far beyond what we can observe, which is quite plausibly true. The next level comes from eternal inflation, the idea that the cosmic expansion that birthed our universe never fully stops, but keeps spawning new bubble universes endlessly, each a self-contained cosmos forever cut off from the others, and crucially, each possibly settling into different physical laws, different force strengths, even different numbers of dimensions. If this is right, there could be an unimaginable number of bubble universes with wildly different physics, most of them sterile and strange, and ours just one bubble that happened to come out hospitable to complexity and life. A third level is the many worlds interpretation of quantum mechanics we met in the story of physics, in which every quantum event splits reality into branches, each outcome happening in its own newly separated world, so that countless parallel realities are constantly branching off. And the most radical level of all proposes that every mathematically consistent structure exists as its own universe, so that mathematics itself is the landscape of all realities. An idea so sweeping, it is hard to know how even to make sense of it. The reason serious scientists entertain these ideas, rather than dismissing them as fantasy, comes back to the fine-tuning puzzle we discussed, the unsettling observation that the constants of our universe seem precisely tuned to allow complexity and life if there is only one universe. That fine-tuning is a deep mystery demanding explanation. But if there are countless universes with different laws, then most are dead and sterile. A few happen to have the right settings for complexity, and of course, we find ourselves in one of those rare, hospitable ones, because we could not exist anywhere else. This combination of a multiverse and the observation that we can only find ourselves in a life-friendly universe is, for some physicists, the most natural explanation of fine-tuning, turning an apparent miracle into a selection effect. The multiverse, in other words, is not invented out of nothing, but is suggested both by our best theories of inflation and particle physics, and by this genuine puzzle about why our universe is so suited to us. But the multiverse runs into a deep and troubling objection that goes to the heart of what science even is, and reasonable physicists are sharply divided on it. By their very nature, in most versions, these other universes are completely beyond our reach, forever cut off, impossible to see, visit, or detect in any way. And if we can never observe them, never run any experiment that could confirm or rule out their existence, then in what sense is the multiverse a scientific theory at all, rather than a piece of philosophy or even faith? Some respected scientists argue forcefully that a claim which cannot, even in principle, be tested has crossed the line out of science, and that the multiverse, however appealing, does not belong in physics. Others respond that the multiverse is not assumed directly, but falls out as a consequence of theories like inflation that we have independent reasons to take seriously, so that even if we cannot observe the other universes, their existence might be an unavoidable implication of physics we can test. This is a genuine, unresolved debate, not a settled question conducted by serious people on both sides. The honest position, then, is that the multiverse is a serious idea, motivated by real puzzles and emerging from real theories that may also turn out to be permanently untestable, and that sits right at the blurry and fascinating border between physics and philosophy. It is one of the places where cosmology pushes hardest against the limits of what we can ever know, asking us to consider whether our entire universe, vast as it is, might be just one of countless others, while acknowledging that we may never be able to find out whether the multiverse is the boldest insight of modern cosmology or an untestable speculation that should be set aside is itself a matter of genuine debate, and how it is ultimately judged may depend on developments in physics we cannot yet foresee. What is certain is that the question of whether our universe is unique or one of many is among the most profound that human beings have ever seriously asked, and that we are, remarkably, in a position to ask it scientifically at all, even if the answer remains, for now and perhaps forever, beyond our grasp. So let us gather up everything and see where we stand on the three great questions we started with. On the first, where the universe came from, we have a genuinely magnificent answer: the Big Bang, supported by three independent pillars of evidence and accepted by essentially every cosmologist, telling us that the universe began about 13.8 billion years ago in a hot, dense state and has been expanding and cooling ever since. We can reconstruct its history in remarkable detail from the first few minutes onward, and that is one of the towering achievements of the human mind. But we also know exactly where this answer runs out, at the very first instant itself, which our physics cannot yet describe, leaving the ultimate question of why there is anything at all still open, perhaps to be answered by inflation or a cosmic bounce or something we have not imagined, or perhaps never to be answered at all. On the second question, what the universe is made of, the honest answer is humbling in the extreme. About 5% of it is the ordinary matter we understand. the stuff of stars and planets and people. The other 95% is dark matter and dark energy, two profound mysteries that we can measure but cannot explain, and one of which produces the single worst prediction in the history of physics when we try to calculate it. We have built a precise, successful model of a universe whose main ingredients we cannot identify, which is a strange and wonderful place for science to find itself. Knowing the shape of our ignorance with such precision. And on the third question, how it all ends, the most likely answer, given what we know, is the slow, cold fade of the heat death, an ever expanding, ever cooling cosmos, winding gradually down toward darkness and stillness over spans of time that dwarf everything that has happened so far. Though a more violent big rip or a reversing big crunch cannot be entirely ruled out because the fate of everything hinges on the behavior of the dark energy we do not understand. Beyond those, we ventured into the genuinely speculative, the cyclic universes that might bounce forever, the multiverses that might surround us with countless other cosmos we can never see, the holographic principle that hints our solid reality might be encoded on a distant surface, and the simulation hypothesis at the very edge of what could ever be called science. These are not equal to the Big Bang in their support, and I have tried to be clear about that. But they are where the questions lead when you follow them all the way out, and some of them are pursued by serious people for serious reasons. What strikes me most, looking at the whole landscape, is the particular mix of staggering knowledge and profound humility that good cosmology requires. We are small, short-lived creatures on a single planet orbiting an ordinary star in the outskirts of one galaxy among trillions, and yet we have figured out the age of the universe, traced its history back to its first minutes, weighed its invisible ingredients, and sketched its possible endings billions of years from now. That is an almost unbelievable thing for a species to have accomplished in roughly a single century of serious cosmology. And at the very same time, we have discovered the precise limits of what we know, the exact places where the evidence stops and the guessing begins. And we have learned, slowly and against our instincts, to be honest about them, to say we do not know and mean it, rather than papering over the gaps with comfortable stories. There is a real kind of wonder in that honesty, a richer wonder than any tidy final answer could provide. The universe turned out to be far stranger, far larger, and far more mysterious than anyone imagined. And the deeper we look, the more the solid ground of certainty gives way to genuine, open, unanswered questions. The Big Bang, the dark sector, the fate of everything, the possibility of other universes, the nature of space and time themselves, all of it remains a living frontier, with the most important questions still unsettled and waiting. We began by asking where everything came from, what it is made of, and how it ends. The largest questions a mind can ask, and the most truthful answer we can give after everything is that we have learned an extraordinary amount, that we are surrounded by mysteries we are only beginning to understand, and that the universe still holds its deepest secrets close, inviting us, generation after generation, to keep looking up and asking.